In this topic, we're going to be looking at optimization under constraints, theory and applications. In our previous topic, our focus was on optimization problems with more than one variable. So for example, if we had a firm producing two goods, Q1 and Q2, we would identify the quantities of each good that the firm should produce in order to maximize profit, for example. In this topic, our focus is still on optimization problems, but now we are optimizing subject to a constraint. For example, a firm is still producing two goods, Q1 and Q2, but the firm is subject to a constraint which we can think of as a type of restriction. So, for example, this particular firm can only produce a certain amount of units, say a total number of 1,000 units. With these types of examples that we're going to be working with in this topic, we cannot assume that our choice variables are independent. They are no longer independent, unlike in the previous topic where they were assumed to be independent. So in those cases where we did not have a constraint, the choice of one does not affect the choice of the other. So if we go back to our two-product firm producing product Q1 and Q2, they can choose any value for these two products, okay, without the two choices limiting each other. But this is no longer going to be the case now that we are introducing a constraint, because now we will say that the variables are linked, okay, but not in a causal way. So we are not saying that one variable causes the other, not at all, but they are linked. For example, if we have a constraint like this, x plus y equals 100, this is the limit, this is the restriction. X plus y cannot exceed 100. So the more we have of x, the less we have to have of y. Okay, so, and obviously vice versa. So that is how we now are dealing with a situation where the two variables are going to be linked. So a good example of this is utility maximization, where we want to maximize our utility in choosing to consume two goods. We could call them Q1 and Q2. And we are constrained by our budget. Okay, so we cannot consume any amount of these two goods. Okay, we have to be aware of our budget and realize that we are restricted by our budget. So if we choose more of the one good, we have to spend, or we have less to spend on the other. Okay, but we are still working with an optimization problem because we are still wanting to maximize something. And in this case, it will be maximizing utility. All right. The other example that we've already touched on is where a firm wants to produce two goods, but they are subject to a production quota. Okay, so they could say we could be looking at a situation where a firm wants to maximize its profit, but it is subject to a production quota. Okay, and if it's producing good Q1 and Q2, it cannot exceed a total amount of however many units. Let's start with an example. We're going to work with a utility function, and we are told that the utility function looks like that. And the price of good 1, which we are labeling x1, is 4, and the price of good 2, which we are calling x2, is 2. All right, and we want to know how much of x1 and x2 can we buy if we have 60 Rand to spend, and we want to maximize our utility subject to this constraint. Okay, so this is our budget constraint, and it tells us how much we can afford, okay, given that we have a budget of 60 Rand and the unit price of X1 is 4 and the unit price of X2 is 2. And we also know how much utility we will derive from consuming these two goods, okay, or we can work out how much utility we will derive based on how much we consume of each good, and we want to maximize our utility subject to what we can afford with our budget and the prices of the goods. Okay, so we are still aiming to maximize an objective function as we did in the previous topic. Our objective function now is our utility function, but the big difference, of course, is we now have a constraint and we have to take that into account. And in this example, our constraint is our budget. All right, so as we said on the previous slide, the choices of X1 and X2, these are linked, okay? They are mutually dependent. If we want to consume more of X1, we would need to reduce our consumption of X2 and vice versa. Let's understand our utility maximization problem with a few graphs. So starting with this graph here, if we were maximizing utility and we didn't have a budget constraint, then that would allow us to choose any amount of X2 and any amount of X1. Now that we have this constraint of a budget and a budget line, X1 and X2 will be linked. For example, if we only wanted to consume X2 according to the price of these goods and our budget of 60, that would mean that we could only consume 30 units of X2 and 0 units of X1. Now, if we want to consume any units of X1, we would have to reduce our consumption of X2. All right, so it's as we said on the previous slide, if we want to increase the one variable, we have to reduce the other. All right, so we can now illustrate this, the budget constraint as well as the utility function using this graph here. And we have the budget line depicted over here, and we have also drawn utility on this graph. So using the utility function that we saw on the previous slide, for the various combinations of goods, X1 and X2, we can calculate the utility from consuming that amount of goods. So, for example, if we were to consume 0 of X1 and 30 units of X2, total utility in that case, if we measured it here, would be 0. Okay, at the opposite extreme, if we consumed 15 units of X1 and 0 units of X2, all right, so that would be a point like that, then the utility derived, if we plug into our utility function for X1 and X2, utility would be 30. All right, and for any other combination of X1 and X2 that we might consume, we can calculate the utility. For example, another combination that is affordable, X1 8 units and X2 14 units, we would calculate a total utility of 128. And that is what this utility function here, what this graph here is illustrating, the utility associated with the budget line. Okay, so we are showing the amount of each good that we can afford and the associated level of utility. Alright, so a better way to depict this would be to use a 3D diagram where we would say have the x variable, and here we've called it the y variable. Okay, this could just as easily have been labeled x1 and x2, but we've got x and y here, and z is what we're trying to optimize. So for example, in our utility example, we would be wanting to maximize utility. And how we would read off this graph, for a given value of x, let's say a value of x here, and a value of y, let's say at that point there, we would move along to the constraint at the point where these two values would meet, okay, because the constraint is illustrated here, and this is showing what can be achieved. So in the case of utility and a budget constraint, the constraint would be showing what we could afford, and at that point there, for example, with that amount of x, okay, and that amount of y, all right, to see how much utility we would derive from that combination, we need to go up. Okay, and the height of this dome would give us the level of z, say utility, if that was our example. Okay, so what this slice here that we are looking at, this is showing us now constrained optimization, because we are subject to this constraint here. Okay, there's a maximum amount of x and y that we could consume in the case of a utility example, and hence there is a constrained maximum. Okay, and in this case the constrained maximum would be at this point here. Alright, if we could however choose any level of x and any level of y, we would not be constrained and we could reach this free maximum up here. Okay, but in this example where we have, say, a budget constraint, we would not be able to afford to consume at that point there. Alright, so this is the difference between what we are doing in this topic, looking at a constrained maximum, compared to the free maximum that we looked at in the previous topic where we did not work with a constraint. Alright, and just to point out, the constrained maximum cannot exceed the free maximum. Generally, the constrained maximum will be lower than the free maximum, but sometimes they might be equal.